In this lesson, we shall look at linear algebra, MAM2000 W2LA, and we are getting started right now. We shall look at a lot of questions, but our focus today will first be on linear transformations, and also will build up on what we call inner product spaces and other related linear algebra concepts. We're getting started right now. Right, so we shall start by looking at the questions on linear transformations. Question 3 is on linear transformations. It is a map. So we let T be a map from the vector space of all 2 by 2 matrices with real entries to the Euclidean space of the fourth dimension. And we let T be a linear transformation such that the images are defined here as given. We need to find the image of an arbitrary 2 by 2 matrix, and we start to solve this question as follows. There are a couple of ways we need to take into account, and one of the ways to solve this particular question is to start by considering the matrix AB, CD. Okay, we consider the matrix A, B, C, D. And what do we then do? We break it up into a sum of 4 matrices, like so. Okay, it's just one way to do the question. 0B 0 0 plus 0 0 0 plus 0 0 0 D, like so. Okay. Right, so these metrics can be written in that form. I mean, this is just one method to do the question, but there are many tons of other methods to do the question. So what do we then do with this? So what we then do with this, we break it down into a sum of this. So with A, B, C, D like that. And we can factor out the A and write it like that. Next, we factor out the B and write it like that. Next, we factor out the C and write it like that. We at last factor out the D and write it like so. Okay, this is good news for us. And then what do we do next? What do we do next is to take the image. Right, so because we want to find the image of this, so the image, which is T of the A, B, C, D. So now, because A is a scalar, we take A, and this is a linear transformation. So it is such that it actually, the scalars go out of the map, like so. And we actually have C that goes out of the map, 0, 0, 1, 0. We have D that goes out of the map. Okay, so this is what we do in this case. Now D is a scalar, and we have 0, 0, 0, 1, like so. Right, and upon careful examination, we are able to make the following observation, that this indeed is what happens. But what then do we do with this? We actually proceed to simplify this. And we then have been able to obtain T of A, B, C, D, which is A T of what? Of the 1, 0, 0, 0. Right, 1, 0, 0, 0. We have B. Right, so we continue with the T of B. What is B? B is the 0, 1, 0, 0. Good. So 0, 1, 0, 0. We have next C, which is 0, 0, 1, 0. We can see the 1 is in the place of the C here. And at last, we have T, which is the 1 is going to be in the place of the D, position of the D, which is 0, 0, 0, 1, like so. Okay, now this is awesome news. But what is the meaning of all this stuff we have just written on the board here? So this means that with A, B, C, D, we take the images. Now, the image of the 1, 0, 0, 0 is actually this one here. So it's going to be A. We have 0, -1, 1, 0. Like so. Plus, what is the image of the 0, 1, 0, 0? It is this one. 0, 1. And then we have the image of the 0, 0, 1, 0. And that is 1, 0, 0, -1. And then D of the 0, 0, 0, 1, which is 0, 1, -1, 0. So, okay, so it is exactly this. Why are we even writing these matrix B like this? Okay, because these 2 by 2 matrices are members of what you call the canonical basis of the 2 by 2 matrices. Okay, and so there are 2 bases we're dealing with here. So the domain, which is the 2 by 2 vector space of 2 by 2 matrices, has this basis that generates this particular vector space, but also R4 is generated by the images. The images themselves must be images of a basis. Okay, there are many bases of R4, but at this point, the examiner gave us this, but we know very well that we have what you call the natural basis of the 4th dimensional Euclidean space. Okay, now we proceed with the simplification. So this means we have the image of the A, B, C, D. Right, so what is all this stuff here? We write it like so. A by 0 is 0, and then we're going to have minus B plus C. Right, so we can be able to write minus B. Yeah, because the A by 0 is 0 and the D by 0. Yeah. So we have the minus A here together with D. Right? So we have minus A together with D. Like so. Next, we continue to analyze this even further. Right. We want to get the rest of the argument. So this is going to be exactly A minus D. Well done. A minus D. The next one. So now there's going to be a B here minus C. Okay, so this actually becomes the image of the 2 by 2 matrix. The 2 by 2 matrix has this image here. Okay, so what is all this here? This is the answer to the question. This is the image. This is the image. So, right, so at this point, we were interested therefore in finding the image, and this is the image, and we are most certainly done with this question. And now we can conclude this question and say this therefore is the result to the question. And I believe it's very clear and very, very easy. But once again, there are many other ways to do it. And this is just the easiest way, where we write this vector as a linear combination of the basis vectors in the domain space. Okay, so that's something that is very important. Right, let's move on to the next question. Right, so the next question is as follows. Okay, that was just 1 mark. Right, and there are too many questions. The next question is about the kernel of T. Right, obviously to find the kernel of T, we need to remember something. We recall that the image of the 2 by 2 matrix is given by what? Right, A, B, C, D, like so. What is this image? Okay, we got it just right now, and it is exactly minus B plus C.
Minus A plus D.
Well done, minus A plus D. Also, A minus D. All right, and then B minus
C.
Good. This is the image, and this is how the linear map, the linear operator, is defined. But now we need to find the kernel of T and a basis for the kernel of T. How do we find the kernel of T? Right, to find the kernel of T, we proceed as follows. Right, for the kernel, we'll let the image, which is the image of the A, B, C, D, be exactly the same as minus B plus C minus A plus D. A minus D, B minus C, right? We let these be equal to the zero vector with 4 components, 0, 0, 0, 0. Okay, so that is what we do. And the meaning of this is that if you let this be the zero vector in the image space or in the codomain space, right, we're able to see that minus B plus C is 0, minus A plus D is 0, A minus D is 0, B minus C is 0. Okay, now this is exciting news for us. But what then does this mean? Well, this means that from this, we can actually be able to write a simplification. We can see that the first and the last equations are the same, meaning that we can just use the first one and say that B is equal to C. Okay, the first and the last are the same, but also we can see that the second and the third equations are the same, meaning we can use any of these. We can decide to use A minus D equals 0, giving us A equals D. Okay, so we actually can see that this actually simplifies to the two equations there. Okay, now what there is the meaning of this? Now we are able to therefore make the observation that these particular symbols themselves are essentially very, very free symbols. And it means, therefore, we can make the observation that B equals C, but yeah, we can give it the name T, it's very common. And A equals D, we can give them as the name, where T and S themselves are real numbers, like so. Okay, right. So we have T and S themselves as members of the real vector space. Okay, now good. What then all the fields here of real numbers are there? Okay, so now what then do we do? We take this and we want to find a basis for the kernel, right? So thus we make the observation that at this point we have the kernel of T, which is given is what, right? So in other words, we can actually be able to see that the kernel of T, right? So the kernel of T contains the members of the domain, right, which are the 2 by 2 matrices, right? Remember that the kernel contains members of the domain, so it contains what? It contains the matrices of the form A, B, C, D, such that, so it contains A, B, C, D. You can write a little bit more. Just write one statement here, very trivial though. Right, you can write one statement that's very trivial. So it contains the 2 by 2 matrices such that these are elements of 2 by 2 in R, such that the image of the A, B, C, D is the zero vector. Okay, so yeah, so the kernel is defined like this. And how? So it contains the 2 by 2 matrices whose image is 0, which is exactly what we have mentioned here. So now, which is sort of the null space. This is called the, yeah, if you don't want to call it the kernel of T, we call it the null space of T. All right, so right, so what is it exactly that we have? So we have made this equal to 0, and therefore it means that wherever there is A, B, and C, we can put T, because B equals C equals T, right? So B equals C equals T, but A equals D equals S. So wherever there is A and D, you can put S and S, right? And wherever there's B and C, we put T and T, like so. Okay, now this is awesome. And then now we are able to see that, Mr. Examiner, this is true, but it is true such that the S and the T themselves are members of the real numbers, the field of real numbers. Okay, what is all this here? Right, this is exactly the same as what? Right, we perform further simplifications of this. So, yeah, so we get the kernel, which is exactly this, but this kernel can be written very, very beautifully, because we want to find what? The kernel of T and a basis for the kernel. So now this is this is already the kernel. So this one is the kernel, right? So it is the kernel of T, or sometimes some books call it the null space of T, right? Or you can call it the null space of T, where you write null of T. In this case, null of T would actually be this set here. Okay, right, the set has been written exactly in set builder notation, set builder notation. Now, we take these then into account and we perform further simplifications using algebraic concepts as follows. Right, so if we then continue to then say the kernel of T is exactly the same as TS ST, such that S and T are members of the real numbers. We then continue to then say the kernel of T is TS ST, such that S and T are members of real numbers. And therefore, what is this? We can write this one as TT00 plus your 0SS0, like this. And this is true such that S and T are real numbers. What is this? We can factor out the T from the first matrix and write it as 1001 S0110. ST is an element of the real numbers. Now, this then can be seen as the span. Right, so it is the span of 1001 together with 0110. Like so. So this is the span. But now if the span is this, we're able to say the following. So we're able to make the observation that the kernel of T is actually this particular span here. So it's spanned by this. So we're able to see that actually the kernel of T is actually spanned by, so now span means just a set of all linear combinations. And the linear combinations themselves are these ones, the 1, 0, etc. So we write here the 1001 together with 0110, like so. Okay, now what is this stuff here? A basis. We're able to make an observation that a basis for the kernel of T, right? Basis for the kernel of T is, for instance, okay, we can write many bases. All right, okay, normally the bases are many, but now we like here, well, it doesn't matter. Right, at this point, you can just take these here. Okay, but we need to check for linear independence of this. In principle, we need to check that these are linearly independent from the span, and it is easy to check that. So we're able to observe, therefore, that this 1001 0110, right, this one here, a basis for the kernel is, for instance, this here, and this becomes a basis for the kernel. So there are many bases that one can give, but this is just one basis for the kernel of T, or for the null space of T. Okay, the null space emerges in many ways. We have actually the null space of T here, just a null space of T, but there are many null spaces there. And we proceed to even investigate more problems, but also we are able to analyze these even better. So what have we done in B? We've found the kernel of T, and we've found a basis for the kernel of T. And the word A, this A, the use of A means that there are many bases. So just wrote one, but there are many equivalent. You can multiply this by a number here, etc. And it will still be the same thing. It will still be correct. Okay, now let's look at the next question.
Can I ask something?
Yes, please.
So with the kernel, we always set it to the zero vector. We always set the transformation to the zero vector.
Yes, you always equate
The
the
image.
linear transformations to the zero vector. Always a zero vector. Okay, always
Okay.
a zero vector. Right, always a zero vector. The zero
Okay.
vector that sits in the codomain. Okay, the zero vector sits in the codomain. Look at the next question. Right, look at the next question. Right, the next question is very interesting and very nice. Find the range of T and the dimension for the range. Like we found the kernel and we found the basis for the kernel. And we could therefore speak of the dimension of the kernel, but they did not ask us. But the dimension of the kernel becomes the number of members of the basis. In this case, the dimension of the kernel would have been what? Just to look at that. So at this point, the dimension of the kernel did not ask us, but now we could say, Mr. Examiner, would ask us the dimension of the kernel would be the number of elements in the basis, and it would be what? It would exactly be
Which is 2.
Right. So, but yeah, but they did not actually ask us to do that. It was just in an exam, so they can't ask all questions possible. But now we have a chance to do the next question. Right, let us analyze the range. The range is actually nothing other than the image. Okay, so now we're interested in dealing with the image of the linear transformation. So at this point, we want to find the range, but let us remind each other because we need to remember what we just said right now because the ABCD is the map, the linear map, whose image is known very, very well. It is exactly minus B plus C. It is exactly minus A plus D. It is exactly A minus D. It is exactly B minus C. So this is exactly the image of T. Now, we want to therefore find the range, and the range is something very, very easy, right? So what then is the range of T? Right, so the range of T, we start and say, okay, we want to find the range. Right, so the range of T is actually a subset of the, or at least it is a subset of the codomain. So in other words, the range of T would therefore consist of all the vectors in R4, right, with the image defined. Okay, so now what then do we do here? It contains the images in R4. So at this point, it actually contains what? Right, so at this point, then you're able to see that it contains the members of R4, which satisfy this particular equation. Right, so then if this is true, it means therefore that the range would contain these guys. So it would contain minus B plus that. Okay, so yeah, you can say, let me just, okay, there are many ways, but let me just write it like this. Okay, I think it's nicer. All right, so the range of T would contain the set of the images. So it would contain the A, B, C, D, like so. Right, such that the A, B, C, and D themselves are members of R. Okay, you can write like this. Okay, so obviously it contains the images of T. So T itself is a map from the 2x2 matrices to R4. So it contains the images of T, and the images of T look like this. Okay, now, what is this? So the TABCD will therefore be the same as minus B plus C, that is the image, minus A plus D, that is the image, and A minus D together with B minus C, like so. And this would be the B, the C, the D, B, C, D. Okay, let me write all of them properly in some order. Okay, let us assume some order here. Otherwise, we're not we're writing things the mixed up, doesn't really matter. We can juggle up the symbols, but we have a perfect chance to write these in order. So we can say, for instance, the A, B, the C, the D themselves are members of the real numbers. Okay, so we can write like so. Okay, where we have the A, the B, the C, and the D are real numbers. Now, what is all this stuff here? This stuff then is what? This stuff then means that we need to take this into account and simplify. Let us do some little simplification here. So the little simplification would be that, okay, we make the observation of the similarity of these particular arguments here, right? The similarity of these particular arguments, but also let us see what we have here exactly. Right, so if you look very carefully, you are able to, okay, there are too many ways to do this one. But now, like we did for the kernel, we can break it up according to the what is popular here. Like you have the B, okay, like you have B here. Is there any other B? Okay. Okay, there's there's some similarities. Okay, we can do this. We can take out the minus and write B minus C. And then now, I mean, we want to see similar arguments and want to write these very nicely because they are similar. They are like what similar arguments, sort of equivalent arguments. Okay, some differ just by sign. Now, like the first and the last are the same, so we can write here minus. Then we have B minus C. Okay, and then next we take minus and you write A minus D. And then we have A minus D, and then we have B minus C. Okay, you can write it like this. Such that this is A, B, C, D, and these are real numbers. You can write like so. Next, what do we then say? Okay, we can be able to make the observation that this is, the first one we can give the name S. So we can call it minus S, and the next one you can call it minus T, and then this one you can call it exactly S and T. Okay, you can make these observation because we can see that these things differ by sign, but where the S and the T themselves remain real numbers. Now, with this observation, we're good. We're good. Right, we take this into account and then we continue to simplify this. And it then means, okay, we need to find the range of T. Okay, let's take that into account. Okay, we have already done, I mean, we can just go on and on. But we need to find the range of T, and this one here is the range. Okay, this guy is the range. Is the range of T. Is the range of T. Okay. Okay, so we found the range of T, but we need to find the range of T and its dimension. Right, so the next step is to find its dimension. So we find the dimension, and the dimension will be found as follows. Right, so the dimension obviously will be found as follows because we're able to make the following observation. Therefore, that at this point, if we have the range, right, if we have the range of T, which is exactly the same as, for instance, ST, okay, and we have put, doesn't really matter how you do it, but there are a couple of ways to do that. So we have this one, minus S minus T, then ST. Right, so we have minus S minus T, then ST. You have S and T. And then now, if this is the case, what is this? Right, so now you then have that we can be able to separate the letters. So we can have minus S0, S0. We have 0 minus T, 0 T, like this. where the S and the T are real numbers. Next, we are able to take out the S, and we have -1, 0, 1, 0. T, we have 0, -1, 0, 1. Once again, these things are not unique. You can write these in many ways, but they're equivalent. Right, so you have this. Okay, now, if this is the case, what then are we able to make as an observation here? Right, what we're able to make as an observation is therefore that this range here is such that you have the range of T is equal to the span. The span of -1, 0, 1, 0, together with 0, -1, 0, 1. Okay, so in other words, it is equal to the span of this. The next step is to show that this span is linearly independent, and then we can be able to find the basis and be able to obviously, infer about the dimension. But now at this point, these clearly would be such that these two guys give us something interesting, and now we're able to find the basis. So we can say a basis because there are many, right? So a basis for the range of T is as follows. So now we then say a basis, right? A basis for the range of T is, right, what is the basis for the range of T? Right, is exactly -1, 0, 1, 0, 0, -1, 0, 1, like this. Okay, so a basis is this. This is just one basis. Okay, so, but this basis can be such that, you are, right. Let me see what we have here. So this is okay. It's okay. So we cross-check these things. You cross-check these things here. You cross-check these things. It's perfect stuff. Let me see. Okay, yeah, there might be a small typo. Let me just check this. Okay, I want to check something here. And if we were able to do this, there's a small typo here. Okay, just a small typo, just check this. Okay, I'm just looking at the order of the S and the T. Right, because obviously we agree that this is minus B plus C, this is minus A plus D, this is A minus D. I mean, that is the image, but here it's the same. But yeah, so here what is very important is that the first and the last, these ones here will differ by sign. So yeah, it's supposed to be, the S is supposed to be the bottommost, please.
Okay.
Yeah, because it's B minus C here, it's minus B minus C, and then B minus C here. Right, so yeah, just watch that out because I can see that things are a little bit mixed up. So now, obviously, if you have the S and the T here, this A minus D itself is T, and this bottommost is S. Okay, yeah, so it is minus S minus T, TS. Okay, so minus S, okay, let me see. Minus S minus T, then what do you then have again? I need to write the correct things here. Then you have minus S minus T, TS. TS. All right. Okay, now continue. Okay, let's check. Now, at this point, I wanted to write the things correctly here. So what then we're able to get here is as follows. Right, so we have here the minus S, 0, 0, 0 minus T, 0. Okay, wanted to make sure that those things are written correctly. So we have here, okay, we have here, and we change this one here. So this one here will therefore become minus S, 0, 0, S. 0 minus T, 0. You're right. So yeah, let us continue and okay, so we continue. So at this point, okay, let me just also remove this one. So you're gonna remove this guy here. You're gonna remove this guy. So when you remove this fork here, this guy here, okay, you're gonna have here -1, 0, 0, 1. You factor out the t, it's gonna be 0, -1, 1, 0. Okay, this is what you're gonna have. Okay, I just wanted to make sure we have the correct thing here. So now this is exactly what we have, but this is gonna be the span of that. Okay, we want to find the dimension. So now, but before we can. So a basis would therefore be the following. You need to make sure the basis is written correctly. So you'd have the numbers written in sort of the correct order. So watch out. So obviously then the numbers or the coordinates would then be yeah, okay, yeah, okay, but please reach out. Yeah, I meant the range of this. That's right. So okay, please watch out for this here. The span would contain only numbers in the vectors. So it would have -1, 0, 0, 1, and then -1, 1. So we take the vectors for the span. Okay. Right. So I want to put the basis here. The basis will therefore contain the numbers. So we don't put the variables. So we have 0, 0, 1, and then here you have 0, -1, 1, 0. So yeah, watch this space. Okay. So it's exactly what we have. So we've taken these vectors to put them there. Okay, basis for the range is this. Okay. Now this is awesome news. But what then do we do with this? We want to find the dimension. Right. So what is the dimension? Dimension obviously will be the number of areas. So the dimension of the range of t, right? Dimension of the range of t, the dimension is actually 2 because there are 2 vectors in the basis. There are exactly 2 vectors in the basis. So this is exactly what we have here. And this is very, very important for us to take into account. Okay, right. So I believe there is no question, but a very, very interesting question from the examiner. A very, very interesting question from the examiner. Very, very interesting question from the examiner there. Okay. Now, let us continue then to solve this particular problem, but to solve this particular problem step by step. And also, there are a couple of ways to analyze this question, and you can analyze this question in a way that, you see, if you look at it carefully, you look at this vector and that vector. Okay, this vector and that vector. This vector and that vector, how different are they, these vectors? Okay, this vector, if you multiply this one by -1, you want to get this vector. Okay, because you multiply the -1 by negative, you get -1, multiply this one by negative. So you can see that these are repeat vectors. So this vector is the same as that one. Okay, and this is the same as that. Because these vectors are the same, it means that you can just take one of the vectors. So instead of, you see, vectors like this that are like multiples of each other, you take this one. To find the dimension, if they can be this easy, this was like too easy to see. So you're able to see that these and that are the same. They just differ by a factor of -1. Okay, and also this one is 1 -1, and this one is -1. So you multiply this one by -1, you get these. So you can take these 2 vectors and these 2 vectors will sort of form the basis. Okay, so these 2 vectors will sort of form the what? The basis. And if they form the basis of these 2 vectors, then it would have a basis, and you can just say the dimension of the basis would therefore, the dimension of the image, the dimension of the range of the image space. Right, dimension of the range would therefore be 2 because there are like two elements there. Okay, so this is something that is very, very important. But you can see what we're getting. We went through so many steps, but so many steps. Another student would look at this carefully and say, I'm going to take this one here. I'm going to take this one, which is exactly this. And then I'm going to take this one, shortcut, which is exactly this. Right, so the student can say, I'm going to just take these 2 vectors and form the basis for the range. because you can see that these are like duplicate, they differ by a factor of -1. So it's exactly what we got, so that the actual basis for the range is 2. So I'm just looking at it from a different point of view there. Let's look at the next question. Right, so in the
So
next,
the range,
yes,
does
yes,
the range contain the variables S and T?
yes, that's a good question. Does the range contain the variables S and T? Yes. The range contains images of the linear transformation. So obviously, that's a good question. But obviously the images of the linear transformation would be such that, remember that linear transformation is defined like this. So the image has variables. This is the image. So the image of this contains variables. So in which case, therefore, the range would contain the variables as well. But I mean, yeah. So there will always be variables for this particular question because the image itself has variables. Okay, so we're good. But as I was saying that they are the span contains vectors with
Only
constants, numbers, number entries, components that are numbers. Okay, so that's something that is very important there. Okay, we're good. Right. So the next thing we're gonna have what? Right. We're able to see that we have with us the map T. Is T injective? Give a reason for your answer. Is it a one-to-one map? T. Okay, so or with A, B, C, D. Okay. Right, if you have A, B, C, D, you've already seen that this range can be written in many ways. Minus B plus C, that is what we have, minus A plus D, and then we have A minus D, and then we have B minus C. And this, we have been able to write it beautifully and nicely as minus S minus T S T.
No, TS.
TS, well done. Okay. Wondering why these always take that order. Thanks so much for noting that. So obviously it would be TS. Okay, good, because you can see the signs there. Right, so now let us check. Let us check. Okay, I mean, we can write it like this, where the S and the T are real. The S and the T are real numbers. Okay, obviously, we want to make the observation, is T injective? Is it one-to-one or not? How do you know that T is injective? Right, so we make the observation that T is injective. One way to see the injectivity of T, so injectivity of T is because it's like saying T is one-to-one. Okay, it's a one-to-one map. So is it one-to-one or not? We make the observation T is one-to-one when the kernel is the zero vector. All right, the kernel contains only the zero vector, does not contain other things there. Right, so you continue. We continue. We continue. So at this point, we have the following. We have the following. Okay, now is it one-to-one? How do you know? So you must just check the kernel. You must just check the kernel. And the kernel of T must contain the zero vector. So, but we know that the kernel, before we answer that, we've already got the kernel. Okay, so yeah, there are many ways to write the kernel we've got. But, right, so the kernel is, we got the kernel to be ST. Yeah, sorry. We got it to be TSST. TSST says that S and T are real. Okay, kernel of T would be this, where these are real. Now, you ask the question, okay, this is the kernel of T. Is it injective or not? So now, one way to look at that is we have been able to make the observation. I'm not going to waste a lot of time here because we've already made a couple of observations that this kernel would contain the span 1001. Okay, for the T, and then you have 0110 for the SS diagonal. So these you can write like this. But this makes us observe that the basis for the kernel has like 2 elements. So now it means that we can answer this question now. Is T injective? Well, no. T is not injective. Okay, for injectivity, one way is to look at the basis for the kernel. So T is not injective. Why is T not injective? Since the kernel of T does not only have the 0 vector, it has like 2 things. It has like 2, it is dimension 2. Okay, there's like 2 basis elements. Because of that, then we can say it's not injective. It is only injective if one-to-one we look at the kernel, if the kernel contains only the 0 vector. It happens sometimes in some other problems, but in this case, it is not injective there. Okay, so we're good for the 1 mark. All right, is T injective? Give a reason for your answer. We look at the kernel. Right, let's look at the next question. The next question is about surjectivity. Is it surjective? Is T surjective? That is the question. Right, is T surjective? Give a reason for your answer. Now, surjectivity has to do with the image. Now, a map is surjective, or just a function in general. In particular, this is the surjectivity is not only when it comes to linear maps or linear transformations, but also when you're dealing with functions in general, even functions from school. You know, we speak of a surjective function. Is the parabola surjective? Is a straight line y equals mx plus c from high school surjective? So I mean, this surjectivity. So what does surjective mean? It means that for every, we start from the end. We pick an element here, which is an element of R4. For every element y in R to the 4, we can get an element x such that Tx is y. Okay, so can we be able to do this? In other words, we claim that a map is surjective if we do not have superfluous elements in the codomain, such that you can pick them. But now, if you pick an X, there's nothing that is mapped into it. So they're like loose elements. Okay, but now we answer the question. Is it surjective? So obviously, let us look at that. Now, for it to be surjective, we need to look at the dimension of the range. And we already know that, I'm not going to waste a lot of time there again. So the dimension of the range of T. What is the dimension of the range of T? 2. The dimension of the range of T is 2. Okay, so we compare that with the codomain and the dimension of the codomain. So we compare that with the dimension of R4. What is the dimension of R4? Dimension of R4 is good. So we make that comparison to then say, how do these things compare? Okay, if T is surjective, then the dimension of the range must be the same as the dimension of the codomain.
Sorry, please repeat that.
Right, if T is surjective, then the dimension of the range of T must be the same as the dimension
of the codomain.
of the codomain. Okay, this is like the codomain. So at this point, you can see that they're not equal to each other. And that means automatically we know that it's not surjective. So is T surjective? No. T is not surjective. Right, so T is not surjective. Why is T not surjective? T is not surjective since we compare the two dimensions. The dimension of the range of T, right, so we write the dimension of the range of T and we compare it with the dimension of the codomain of T. So the dimension of the range of T is actually 2, and 2 is less or equal to the dimension of the codomain up there. Okay, so it's less or equal to that, so we can, yeah, okay, just as strictly last, let us be very strict with our inequalities here. So at this point, we make the observation dimension of the range is 2, but 2 is strictly less. Can I say that? It's strictly less than 4. Okay, 2 is more than 4. They must be equal to each other, but they're not. 2 is more than 4, where the 4 is actually dimension of the codomain. So nicely written there. So obviously we can see dimension of the range is smaller than dimension of the codomain. So therefore this makes us say that T is actually not an injective linear transformation. Okay, so any question?
No.
No question. So we good. We're good. Let's look at the next point, F. Right, next question is F. Right, so we look at the question F. Question F. Question F. All right, so F is this one, and we still have the same sort of restrictions about the linear transformation is defined, the images are defined like that. So we need to find a matrix. A matrix with the subscripts C and B representing T with respect to the ordered basis. So there are two ordered bases, the ordered basis B and the ordered basis C. Ordered basis C is the canonical basis or natural basis of the image and of the codomain. And the basis of the domain space is actually this one here. Okay, now we are saying we want to find the matrix T. Let us find the matrix T. Right, to find the matrix T, we proceed as follows. To find the matrix T, we proceed as follows. Now, we need to remember a couple of things here. Now, to find a basis for this here, we write, because once again, this is called a matrix representation. So you want to find a matrix T representing T with respect to the ordered basis. But we understand that T itself is a map from the 2x2 matrices to the to R4. Okay. Now, to do this question, we write matrices as a linear combination of other matrices. For example, if you take this one, can it be written as a linear combination of, in terms of the map T, a linear combination of certain images, for example? Right, because in the end, we are making the claim that we can be able to do this if we're able to write, because every vector in our in M22 R can be written as a linear because this is a vector space. So every vector can be written as a linear combination of other vectors. Okay, right. Let us analyze these together. So at this point, we would then continue to then say, can we be able to write? Okay, here it is with much ease. There are many ways to do that. But we need to remember that the T1000 has this image. And we would, let me see if I can just maximize something here. Right. Let me see if I can, yeah, okay, I'm sure that it will. So now we are making the observation that at this point, if we can say this 0010 can be written like this, and the 001 can be written like this, and the 0100 can be written like that. Now, what then are we able to say there about any vector? So now we're able to make the observation that every vector, like this vector, can be written as a linear combination of the basis vectors. And with that then in mind, we can be in a position to do what is required. So now, if we are to look at this, I want to discuss this a little bit more elaborately. So if you are to look at the fact that here is C and B. So now, in terms of C and B, C, so now we are looking at the fact that, let me just write it like this. Right, so we are mapping B to C, okay, because, yeah, we are mapping B to C because we're taking the 2 by 2 matrices to R4, these column vectors. Now, if this is the case and that is what we are doing, we are able to note, therefore, that every vector can actually be written exactly in that form. Right, so even if you take an arbitrary vector, any arbitrary vector can actually be written in the required form. So thus, if you then take, okay, there are many ways to do that, but also we can write it more elaborately. We can write it. So let us analyze these together. So if we are mapping B to C, B to C. So in other words, we're mapping B to C. So in other words, it means therefore, every vector can be written uniquely as a linear combination of those particular images. Right, so, and if this is true, then what then would that mean? So it means that the 1000, but it's ordered. It's ordered. Okay, because it's an ordered basis, therefore it means that we shall look actually at the first vector. And the first vector, therefore, can be actually written as a linear combination of the 4 vectors on the image side of things. And then if this is true, then it means we shall actually be in a position to have the image, which is exactly associated with the 1000, and the image associated with the 1000 is exactly that one there, which is 0, minus 1, 1, 0. The second one, right, the second one, which is the 0100, we have the image, this one, which is minus 1001. The third one, 0010, would be 100 minus 1. The last one, 0001, 01 minus 1, 0. Okay, so this would actually be what we are able to most certainly be in a position to express, right? Be in a position to express. So this therefore becomes something that is actually extremely important. So, but There are many ways to reason this out. One way to do this is to use a general formula, as much as we've been able to do this, but you can use a general formula, which I would like us to sort of discuss in view of the fact that if you look at the fact that the t itself, okay, the t of the that we got, the rule, the map, I want us to discuss this a little bit in detail. A, B, C, D. There's a discussion we can have here. Okay, so this one, minus B plus C, minus A plus D, A minus D, B minus C. Okay, this is sort of the rule. Okay, and I want us to be able to use this rule correctly. I want us to be able to use this rule in connection with the vectors we have. For example, if then we have these particular vectors as the image vectors, can we be in a position to write this one as a linear combination of these particular vectors? Now, if yes, how so? Can we be able to do that? Okay, I want us to write, for instance, T of A, B. We've already done it, but I want to write a bit more, this in more detail. Okay, because you see the order. To say the first would have its first image. The 0, 1, 0, 0 would have the image of that. The 0, 0, 1, 0 would have its image as that. And the 0, 0, 0, 1 would have its image as that. But now we are able to then say, okay, what then is all this here? We can be in a position to deal with the images. And we say, if this is the image, what then exactly is this? Okay, let us look at these very, very carefully. You can split it up. Like, you can have the minus B and the B. Okay, let's look at the A. A is this. So 0 minus A, that. What about the B? Minus B, 0, 0, B. What about the C? 0, 0, C. What about the D?
Or is it not negative C?
Well done. For the bottom C, it's negative. Okay, well
Yeah.
done. Right, the D would be 0, D minus D, 0. Okay, you'd have something like this. Something like that. Okay. Something like that. Okay, so we can write this exactly. Or if we don't want to write it like this, how else can you write it?
Oh, this is the general formula, right?
Yeah, this is the general formula. This is the general formula.
Okay.
Okay, if this is a general formula, right, so I'd like us to, okay, there are too many ways to do it, but yeah, there's a nicer way to do it. Yeah, we can write it like that, but I want to write it more nicely. Allow me to start from the foundations of this a little bit. I want to just go back to the foundations of this way of reasoning. Okay, first, we take A, B, C, D. We take A, B, C, D. Okay, if we take A, B, C, D, we can be able to write it as like we saw. Okay, we're not going to waste a lot of time there. We've already written like this. Okay, we write it in terms of the bases. All right, so
Okay.
Okay, right, you can write like this, and then you can write it as 0, 1, 0, 0, and then 0 for the B. Okay, so the B is here. The C is here. So if we want, okay, which is 0, 0, 1, 0. Right, 0, 0, 0, 1. Okay, suppose you have this. You have this. You have this. Okay, good. Good, 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 good. Now, we can write this like that. But if we're able to write it that way, simultaneously, we're able to make certain observations in terms of the image. Okay, because the image of the ABCD would be A times the image 1, 0, 0, 0. B with the image 0, 1, 0, 0. C with the image 0, 0, 1, 0. D with the image, okay. D with the image 0, 0, 0, 1, which is A. What is 1, 0, 0, 0? Is this one?
It's
0 minus 1, 1, 0.
yes.
Okay, which is just the same thing as what we're doing before, but we're just doing it differently. Like the 0, 1, 0, 0 would be minus 1, 0, 0, 1. Good. And then the C would be the 0, 0, 1, 0. 0, 0, 1, 0. Is this what is 1, 0, 0 minus 1? 1, 0, 0 minus 1. D would be the last one for the T. 0, 0, 0, 1. 0, 1 minus 1, 0. Okay, would have the image written like that. If this is the case, right, we are then now going to use this rule to analyze our work. Okay, now I want to write these as the A, B, C, D. And then you have A with this one, 0 minus 1, 1, 0. 0 minus 1, 1, 0. B, minus 1, 0, 0, 1. C,
1, 0, 0, negative 1.
yes, well done. Sorry, yeah, well done there. Let me just write this a little bit clearly here for anyone who is going to be able to watch this video. So now we are dealing with the C part, and which is 0, 0, 1, 0. 0, 0, 1, 0 is this one, which is 1, 0, 0. 1, 1. Good. So we come here and say 1, 0, 0, minus 1. Appears we have it right. And then D. What is D? The D part would be 0, 1, minus 1, 0. 0, 1, minus 1, 0. 0, 1, minus 1, 0. Like this. Okay, so I mean, if this is the case, we then now want to use this rule to then say, if we are mapping from B to C, we're mapping because B is the 2 by 2 matrices, and we're dealing with 2 by 2 matrices to R4. So we're dealing with the 2 by 2 matrices to C. So look at the notation. That is, okay, there are too many notations in the books, and yeah, this is just what I'm sure your institution uses. So which means that you'd have A, okay, yeah, so you can use this rule. And I want us to use this rule with the zeros and the ones. 1, 0, 0, 0. Okay, so it's A, B, C, D. A. So you can put a 1 here. 0 minus 1, 1, 0. And then the B, the C, and the D. Okay. Yeah. So here it's only A that is 1. So the rest are 0. So these things are going to disappear. Okay. They're going to disappear, all of them. So we're going to have just one vector like that. Okay. Yeah, but this is nice. Very interesting. Right, so if this is the case, yes. Okay, let's write the images. Okay, yeah, I'm going back to the first principles of these now, just clicking in my mind that you can write it nicely and make sure that in the exam. So what you do is you look at all the images. Okay, so the next one is we started with the 1, 0, 0, 0. Okay, so this is how we do matrix representations in general. So you look at all the images when T acts on the basis vectors. So it acts on this one and you get this image. It acts on this one, which is 0, 1, 0, 0. And you get the image. What is the image? Okay, so the image would be where this component is 1. This component is 1. What component is this one? So it's when B is 1.
B.
Yeah, when B is 1, then you're going to have only this one. -1, 0, 0, 1. Okay, I'm just trying to, okay, I don't want to very long there. So now we deal with the third one. 0, 0, 1, 0. Okay, now if you look at the 0, 0, 1, 0, 0, 0, 1, 0, the 0, 0, 0, 1, 0 is when C is 1. Which is exactly this still. So yeah, it's like we're doing nothing, but because we're getting this exactly. Okay, because we're getting exactly the things we got, but there's something more I want to say. Okay, right. So obviously, if you're dealing with the last one, when you have the D here, then it's when D is 1, then you're gonna get a 1 here. So it's exactly this one here. Okay, so which is the A, B, C, D. Okay, there's something I want to say, but what the matrix representation is by definition, right? So which is 0, 1, -1, 0. Okay, now with these images, so we found the image of each of these basis vectors. The next thing that we need to do, and which is what
Sorry, with the last one. Is it the image of A, B, C, D, or it's just the image of 0, 0, 0, D?
I'm happy that your eyes are open. Okay, so it is the image of the very last vector, this one here, which is 0, 0, 0, 1. Thanks so much for realizing that. Okay, glad that at least you are focused. That shows me that you're focused. Okay, now with these then mentioned, we're good. But now let's take these things into account. And what does metric representation actually mean? Metric representation means that when you have these images like this, each image can be written as a linear combination of this. Okay, we're gonna do just one of them. Let's do the first one. And then, yeah, because they become a little bit tedious. These things become a little bit tedious. So you have 1, 0, 0, 0, 1, 0, 0, 0, like this. Okay, so, but now we write it like this. 0, -1, 1, 0. 0, -1, 1, 0. Okay, so yeah, we're dealing with just the first one, this one. Okay, its image is this, and we can see the image is that. Right, but now in terms of, we must write it as a linear combination of this. Right, so if write as a linear combination of that, it means that you can call it P of the first one. We just use some letters. Q of this one. R of the third one. Okay, depending on the amount of energy, you can do these for all because there are 4 vectors here. So P, Q, R, S. 0, 0, 0, 1. Like this. Okay, if you add all these vectors, which is P, Q, okay, you can add them. R is going to be this, and the rest are 0, 0, 0. It's only R here. You know, you can like that. And then this one is 0, 0, 0, and it's only S. Yes. Okay, so this would mean that at this point, you compare the coordinates of this with that. Okay, in a nutshell, what we're saying is the 1000, don't want to be very tedious here, but this is the true meaning of a metric representation, because representing t with respect to this, it's called a metric representation. So this metric representation is going to be that this vector is like this. Okay, let me just write like that. Okay, now with P, okay, P is equal to what? If you compare, P is equal to the top one, 0. Q is equal to -1. R is the third one from the top. S is 0, bottom one. Okay, so what you do? What do you do with these things? These things, you put them here, and these would form the columns of the metric representation as an ordered basis. So we take these things in the right order like this. So now, order it from left to right. Right, so 0, it's a P, 1, 0, 0, 0. The next one, Q, 0, 1, 0, 0. R, 0, 0, 1, 0. S, 0, 0, 0, 0, 1. All right. This is what we have. Okay, we can do this for all the vectors. Maybe we can do the next one. Okay. Now, with these mentioned, we do this for all the vectors. Let us do the second vector, and then we're going to conclude. I'm not going to waste a lot of your time there with all of them. Right. So now we're going to do the second vector. What is the second vector? The second vector is this one. But we already have the rule for it in terms of exactly in terms of this. Right. So okay, you must not get confused in what in terms of what I'm doing here. Okay. Okay, now we did done the first one, dealing with the second one. The second one must not confuse the vectors. It's 0, 1, 0, 0. Okay, let's do that. 0, 1, 0, 0. Don't want you to get confused in terms of what I'm doing here. So the 0, 1, 0, 0, it's this one, has that image. -1, 0, 0, 1. Matrix representation, if you have the image must be written as a linear combination of these others. So which means that you can write X 0, 0, 0, 0, Y 0, 1, 0, 0, Z 0, 0, 1, 0, W 0, 0, 0, 1. Okay, so okay, you must write the image as a combination of the vectors in the codomain. Okay, this is what matrix representation means. Now, and yeah, I'm gonna write this in many ways. Okay, yeah, we're practicing, please just pay attention with it. Okay, right. So when you have that this vector can be written like this, then you do the multiplication, because x by 1 is x, the rest are 0, 0, 0, top, top, top. Right, you can have x. This one is 0, 1 is y, 0, 0, giving us y. 0, 0, z, 0, 0, 0, w. Okay, meaning x is what? Is minus what? Y is what? Y is 0. Z is what? 0.
0.
And then W is what? The bottom one, it's a 1. Okay, this would give us columns of the matrix representation. Right, so which is 0, 1, 0, 0, because you see, this can be tricky in the exam sometimes. So I'm trying to, you must do it normally with this kind of detail, to then say, you can be able to maneuver your way. So you find the images of the basis elements and then write the images as their combination of the codomain vectors. Okay, so now the x would therefore be like -1, 1, 0, 0, 0. What is y? Y is 0, 0, 1, 0, 0. Z, 0, 0, 0, 1, 0. W is a 1. 0, 0, 0, 1. Okay, we got the second column. Okay, yeah. Okay, yeah, let's just play. We're just doing the last two now, and then we're gonna conclude. Yeah, I want to mention the metric representation. Normally, there's a bit more marks. Hey, you know, they gave it 2 marks because the images are clear, and then you're just putting everything there. I would imagine that. Okay, but in general, sometimes it might not be this easy. Okay.
Okay.
All right. So, well, because everything was given, the rules were given there, and they just thought that you're gonna just put these things there. You don't need to calculate anything quite in detail, but I'm doing a general way of really how we can get the metric representation in general. Okay, so yeah, now let's do the third one and then we're going to conclude with the last one. Yeah, okay, we're doing the image of this one 0, 0, 1, 0. 0, 0, 1, 0 as the image says. 0, 0, 1, 0. Here's the image, this one 1, 0, 0, minus 1. Okay, but now this is the image of this vector. Then write the linear combination of these ones. P, which is 1, 0, 0, 0. Q, 0, 1, 0, 0. R, 0, 0, 1, 0. S, 0, 0, 0, 1. Okay, P is the top one. Q is the bottom one. R, S. P is 1. So you compare this with that. Q is 0. R is 0. And then S is minus 1. Okay, because the matrix representation would contain these scalars as the columns of the metric representation. With that said, we have 0, 0, 1, 0, because this is what metric representation means. But I know that here in this question, yeah, I'm gonna even write the metric representation slightly in a detailed way. So you can write it with the images inside. Okay, we're gonna look at that just that very briefly. Okay, just need to a bit more detail there. So the P is 1, and we have everything we've got, the scalars here. So the P is a 1, 0, 0, 0. The Q is 0, 0, 1, 0, 0. The R is 0, 0, 0, 1, 0. The S is minus 1, 0, 0, 0, 1. Okay, now let us do something more. Okay, let's do the last one. Then we're done.
Okay.
Right. So, and yeah, I'm going to mention why we're doing these things we're doing. 0, 0, 0, 1. What is the image of this 0, 0, 0, 1? It's this one here. So they gave us 0, 1, minus 1, 0. And then, okay, we write it in terms of the variables. We use variables. So it doesn't matter what variables you use. Okay, I don't want to use A, B, C, D because we already had those. So we can use X, Y, Z, W. So X into the first vector, Y into the second vector, Z, W. Okay, yeah, the top, the Y, Z, W, because the rest are zeros of these things, okay?
Yeah.
Right, so equate then the top to the top. So X is 0.
Equals to 0.
Y equals 1. Z is minus 1. W is 0.
0.
Okay, so which means that we have T of this one, 0, 0, 0, 1. Okay, yeah, its image is this one they gave us. But in terms of for the matrix representation, Just practice 4 times. 4 vectors, practice 4 times. So the x, therefore, would be 0. The y is 1. The z is -1. Ah, okay, good. Let's just write this one clearly. The z is 0. Okay, yeah, the z is -1, excuse. And then the w is what? W is a 0. Well done. Okay, so that's what we have. Like this. So what is the matrix representation? The matrix representation like this would be exactly T mapping the basis B to the basis C. Okay, you move from B to C. Okay, this is often very confusing, but yeah, you need to get the order right. Normally, you would say you do things because you're moving from the 2 by 2 matrices to the vectors, column vectors. Right, so in this case, you're moving from B to C, and you're moving from the B. What is B? B is these 2 by 2 matrices. You're moving to C, so you are like moving in the opposite direction. Okay, you know that this is sometimes a little bit confusing. But now I want to write it like this. So you have this matrix. I'm gonna make it like a short matrix, but then because you are moving from B to C, you then have the images of B. I don't want to write a lot of brackets there. Write correctly. Right. So now we're gonna do this one first. 1 0 0 0. Next 0 1 0 0. Next 0 0 1 0. Next 0 0 0 1. Okay. Okay. I was then saying what you do is you put the images there. Okay, you put the image of this, the image of this, the image of this, the image of this, because now you are mapping B to C. Okay. Without wasting any further time, you can then be in a position to then say, once you find these images, you can immediately take these ones, or, which is what I think I'm going to do, which is easy. The 1 0, the image of 1 0 0 0. Okay, yeah, but I wanted to use our initial hypothesis. Our initial hypothesis has been that now the first column of the matrix representation has the 1 0 0 0, whose image is going to be 0 -1 1 0, and then it is equal to the column. The column is going to be having this, that, and that, which is 0 -1 1 0. Okay, which is 0 -1 1 0. So you take the coefficients that 0 -1 1 0. So you take it and put it here. 0 -1 1 0. Next, we look at the 0 1 0 0.
It's -1.
Okay, yes, okay, well done. The 0 1 0 0 would be -1 0 0 1. Okay, so that's what we're going to do. -1 0 0 1. Okay, yeah. And these things are exactly these ones. Okay, if in this one you're able to see that it's going to be 1 0 -1, they're exactly these. Okay, so obviously they gave it 2 marks here because it was easier, but I'm trying to say that this matrix representation is done by really saying that you express the image as a linear combination of these image vectors, and then you just take these coefficients. They then are able to help us form the columns of the matrix representation, where you say find the matrix representing T with respect to the ordered basis, so everything is from left to right. Okay, let us continue now and do more mathematics. So this is matrix representation, y'all. That's already we've just elaborated on that one, and let us look at inner products. right? We have a chance to look at inner products. Now, and in this case, for instance, question 4 has 4 points. On P2, an inner product can be defined by what? Right, so on P2, and what is P2? P2 is the polynomial space of all polynomials of degree 2 or less. Polynomial space.
Yeah, of degree 2 or less.
Yes. Well done, thank you. Right, an inner product can be defined by these. Okay, let's look at the inner product. This inner product is defined by, when you take the inner product of these polynomial of degree 2, another polynomial of degree 2, you just multiply the A2 with B2, you multiply the A1 with B1, you multiply the A0 with B0. Okay, that is the rule. Where these A's and the B's and everything, the coefficients here are real numbers, you need not check that this defines an inner product. Okay, normally there are 4 or 5 properties of the inner product, in which case, therefore, the examiner is saying you need not check that because this thing is 1 mark, so can't be. It's going to waste a lot of time. You are under time constraints in the exam. Let P be this polynomial 3x minus 4 and Q of x be 7x squared. Find the inner product of these. Okay, yeah. It's as easy as it gets. Right. So now at this point, you find the inner product of the Px and Qx. You can just put everything in there. Okay, yeah, it's that. But now you can write it beautifully, Mr. Examiner. You can write it nice. Make sure you avoid mistakes. Write it like the formula says. So because the P has no x squared, so you can write 0x squared, 3x minus 4. Then you have the Q, which is the squared, 7x.
7x squared plus 0.
Good. So you can write it sort of like this. Okay. Right. I'm trying to make sure that you're writing these things like that so that you're in a position to okay. Right. So you multiply the quadratic coefficient multiplied by the quadratic coefficient. So you would multiply 0 by 7 plus 3 by 0 plus minus 4 by 0. And therefore, this is, what is the answer? It's a 0. Okay, check this one. So you'd be actually be in a position to get a 0. So which means, therefore, that this one here, which is the inner product of Px with Qx, you can write it's 0. And therefore, you can actually be in a position to conclude that. Therefore, the inner product of Px with Qx, which is 3x minus 4. And then we have 7x squared. And what is this inner product? It is 0. It is exactly what? 0. Any questions? Okay, yeah, so we've seen that. No. Okay, good. It's very, very straightforward. All right, so we're going to, yeah, we found the inner product there. We're practicing properties of the inner product. The next thing is the length. Right, the next thing is the length, because now we're practicing, if you're dealing with the inner product, you must be able to find the length, what you call the norm. The norm of the polynomial, P of x. Right, so the norm of that is defined as what? Right, so at this point, if you find the norm of P of x, it is actually the same by definition as the inner product of P of x with itself. Okay, so that is the norm of a vector. So even if somebody obviously says, what is the norm of V? It is the square root of the inner product of V with itself. So at this point, if you have the P of x, it's exactly this. So it is, but now we can write it nicely. Okay, because the definition has squares. So you'd have to put the square in the px. So it's going to be 0x squared, 3x minus 4, 0x squared, and 3x minus 4, like that. Okay, so by definition, the inner product of this would be this. So you'd have the square root Okay, so multiply this 0 with this 0. And then multiply the 3 by 3. And then you multiply -4 with -4. Like so. 3 by 3, it's 9. 16. And 9 plus 16 is precisely a good 25. And the square root of 25 becomes exactly what? 5. All right, and good. We're able to make the observation, hence, that the length is actually 5. You can even put some units there, strictly speaking, because it's the length. So now you can say the length is actually 5 units, but yeah, but because this is like too much mathematics, it's not applied math. So yeah, you can just write the 5 like that, even without the units. Okay, because they're just interested in the numbers. It's not a lot of analysis in terms of what the meaning of this is. Okay, there's notations and what comes with that. Okay, so we've found the length of the polynomial px of the vector, and the length is 5. Next question. Right, so in look at the next question, we proceed to try the next thing. The next number. Let's look at the next number. The next number. Okay. C. Right, so let A be a subset of P2 defined by this. Right, so A is a subset of P2. And what would this mean? So A being a subset of P2, it is a subset of the polynomial space with polynomials of degree 2 or less defined by this. So A is defined by this. Find 2 linearly independent vectors in A. Find 2 linearly independent vectors in A. Right, obviously at this point, we are interested in doing this question step by step. So we need to find 2 linearly independent vectors. So at this point, we would have to take this polynomial here. If you take the inner product of this polynomial with this one, the result must be 0. So these are sort of, what do we call these polynomials that do this? What do we call the vectors with the 0 inner products? Okay, we call them orthogonal vectors. Often
okay.
Right, so now we would then say, so we have A2. So take just write this one. You can use other notations. So A1x, A0. So this is just saying there is a polynomial R whose inner product with another with this specific polynomial, x squared minus 2x plus 4. The result is 0. Okay, so the result is 0. Okay, so what is the definition of this here? The definition is going to be that we multiply the A2 with 1. And then we multiply A1 with -2. We multiply A0 with what? And the result is 0. Okay, yeah, just multiply A2 with this. And now we want to analyze what is happening here. Okay, right, so this is A2 by 1, which is exactly A2 minus 2A1 plus 4A0. The result is what? Is 0.
0.
Okay, all right. So at this point, what then would this mean? What would this mean over here? Right, so this is an equation. And this equation is a very nice equation. How many unknowns are in this equation? That's the first thing, because we want to find 2 linear independent vectors. So yeah, but we want to find the values, the value of A2, the value of A1, the value of A0, or values of this. But what are you able to see? What are you able to see? Okay, you see, what you're able to see here is that these things, you can't solve this equation and get unique solutions here. All right, so, okay, because of this, then you need to use your ingenuity to say, the examiner would be very open to many answers from the students as long as the answers work, so that when you take the inner product is 0. So you can take, for instance, A naught to be 0. If A naught is 0, you can take two of them, and then the third one you just calculate. So if you take A naught to be 0, and you take A1 to be 1, once again, this choice is our choice, but you can choose A naught to be 100, and then A1 to be something else. Okay, if we choose A naught to be 0 and A1 to be 1, then we must solve for A2. Take just two of them and then solve the other one. So for the other one. So at this point, we have A2 minus 2 times 1 plus 4 times 0 equals 0, which means A2 is 2. Okay. Right, so, and what would this mean, for example? Okay, this is not the only thing you can take, you can choose. So also, because you must find two linear independent vectors, right? So obviously now you can take any other, you can make any other choices. Like you can decide to say A0 is 1. Not a very nice question, because each student will have their own answer here. Okay, you can't get the same answer. Right, so A naught, because we want to find the values of A2 in an equation that is like 3 unknowns. So you then say you can take A1 to be, A0 to be 1, and then take A1 to be 0. We're just switching this around, okay? But it's not, you can take anything, okay? So if this is the case, let's come here. A2 minus 2 times A1 is 0. A0 is a 1. 0. A2 would be exactly what? Would be minus 4. Because this by this is going to be 0, and then minus 4 is moved to the other side. Okay. Now, let us understand this. Let us understand these. Let us understand this. So now, if this is the case, what then are we able to get out of this? Okay, we put everything into this polynomial. We put everything into this polynomial. So what is our A2 here? So obviously remember that we have A2x squared, A1x, and A0. That is the polynomial. So we plug everything. A2 is 2, x squared. A1 is what? It's a 1. A0 is that. Okay, yeah. A2 is minus 4x squared. A1 is 0. And then A0, it's a 1. Okay, so we get these two polynomials. So these two polynomials were to find two linear independent vectors in A. So now we write the conclusion here. Right, write the conclusion here and say, hence, the two linearly. We can check if they're linearly independent. The two linearly independent vectors are this one here, which is 2x squared. But once again, hey, this question here, it means every student is going to have their own answer, because if you have an equation you need to solve with 3 unknowns, you can't solve it. I mean, you can't have unique answers. So you can just have cases. Take 2 variables, guess 2, and then get the third one. Okay, guess 2 and then get the third one. Yeah, so this would give the equation of a plane in particular. I mean, this, yeah, because it's the equation of a plane, sort of. Okay, right, so hence the two linear independent vectors are 2x squared and x, and also minus 4x squared and 1. We good. We also, right, so we found the two linear independent vectors that do this job. Next question. Right, the next question, we want to deal with bases of polynomials. Right, let us deal with the bases of polynomials. Bases of polynomials, and we look at the next question, and the next question is question 5. Right, so now we're moving to question 5. I know that it appears as if we're not moving, but we're moving. Right, So now, if you answer the following questions, giving the reasons for your answer. Now, let S be a subset of P3 defined by this, where P3 is the vector space of all polynomials of degree 3 or less. All right, and now, what is the dimension of P3?
It's 4.
Well done. Right, so the dimension of Pn is n plus 1. So yeah, I'm mentioning that because if somebody's saying let S be a subset of P3 defined by this. 1, 2, 3, 4. It's a very nice one. It's a subset of P3 defined by this, but a very nice one. Answer the following questions, giving reasons for your answer. Okay, we can say a lot about this. Find a basis B for the span of S. Right, so if you want to find a basis B for the span of S, we proceed as follows. Right. Okay. You need to find a basis B for the span of S. What do we do first to find a basis for the span? Right, so we need to write this linear combination and equate it to 0. First things first, we must take how many vectors? 1, 2, 3, 4. Well, I'm just going to go back to the basics of linear algebra when it comes to finding a basis. So given a set, the span, how do you find the basis? So you must have A, B, C, D. Yeah. A, B, C, D. Okay, so let A, B, C, D be real numbers. Okay, we're dealing with real numbers. You assume here most of the times, okay, we're not dealing with complex coefficients, but yeah, we can have complex vector spaces. Okay, so now, but these are mostly real in this course. So you take A, B, C to be members of R, let that. Then you can write A times the first vector, like we did with the matrix representations. I'm just going to the basics of things. B into this one. Okay, this is how we reason in linear algebra. To find the basis, you take the vectors and check if they're linearly independent or not. If they are linearly dependent, you discard a vector, you throw away a vector, then remain with others. Okay, so now we must check these ones. So you have C, which is 2x cubed plus x, D, which is minus 3x squared plus 1, and the result is what? The result is the 0 vector. The 0 vector would be, okay, 0 vector in P3. Now, the next thing we do is to, is to do what? Is to collect like terms. Okay, that is what the students say. Collect like terms. So that would mean that the x cubed, there's x cubed here, there's no x cubed, there's x cubed there. So which means that there's 4a plus 2c.
Plus 2c.
Yes, so this would sort of be the x cubed. And then now what about the x squared?
It's a
minus b.
Minus b.
Yeah, it should be
minus 3d.
A minus b minus 3d. Well done, thank you. Okay, I'm just going back to the basics of linear algebra when it comes to bases. We write linear combinations, and obviously this linear combination is what the span means, but now the span means this. Right, so now, what about the linear things? So you'd have 2b plus c, okay, which is 2b plus c, and then there's no other x. There are only two x terms, this one and this one, two linear terms, and then it's times x. What about the constants? What about the constants?
It's just one D.
Yeah, yeah, the well done to you. It's just D. Okay, so yeah, you can write it like that. Can write it like that. Just D. It's only one. Well done. And this result is 0. Okay, I want to write the 0 differently because now we're dealing with the 0, but this 0 is awesome. So now for the x cubed, we would have what? Right, so you'll be able to write 0x cubed 0x squared, 0x plus 0. So the zero vector can be written like this.
Okay.
Okay, yeah, you can write it as a polynomial in P3. And then now it means that we have 4a plus 2c by comparison, it's 0. A minus b minus 3d, 0. 2b plus c, 0. D, 0. Okay, that is what we have. The next thing is to find the scalars here. Is to solve for the a, b, c, and d. That's what we're trying to do. Because we write this linear combination and then try to solve for this. Because if it's a basis, then it means that these things must all be 0. Then all these are linearly independent vectors. And then we have a basis. But now we want to solve for the a, b, c, and d. So to solve this, we use matrices. We use matrices. Right. So the way we use matrices, how to use the matrices. Right. Let us write let us write this matrix like this. Right, because now we can write A, B, C. Well done. So we write the matrix like this. Then we write for the first equation, there's a 4 for A. C, it's 2. And then 0, 0. For the second equation, we have A as a 1, minus 1, C 0, and D is minus 3. For the third equation, 0, 2, C 0. For the third equation, 0, 0, 0, 1. Okay, so this is what we get. This is what we get.
What?
Is it correct, this? Well, you see, the order does not matter. The order does not. Yeah, let's see. The bottom one is 0, 0, 1. I mean, I'm just checking if this have been is correct in terms of we have don't put zeros where they need not be, you know. So it appears that it's pretty fine. It's pretty fine.
It's one there.
Where is the one?
Under C, the second last row.
Yeah, okay, yeah, thank you so much. Well done. There are no letters inside the matrix. Okay, this one is a 1. Okay, anything else to change? Nothing to change. Okay, obviously we want to solve for the A, B, and C. Yeah, the examiner was very, very unkind here. Right, it was very, very unkind. Yay. Okay, so we can row reduce this.
Yes.
Okay, we can row reduce this. Right, to row reduce this, we need a 1 here. So we can say row 1, row 2. Okay, I know that your school might be writing the things different. I think I saw in the notes, you might be writing the things, the row operations under the arrow here. Okay, stacking them up. Okay, I'm just going to check that because I think I looked at your study guide. You can use those. Right, so but you stack up, then this one, you interchange row 1 and 2. You just need to put a 1 here. Then you have 4, 0, 2, 0. You have 0, 2, 1, 0. But it just that Anton and Rose normally puts the row operations on the side of the matrix. So yeah, but you see, there are many books for those. Okay, so now with this, then we're good. Let me just remove this. Okay, you need to put it close a little bit. So we said row 1 is to be interchanged with what? With row 2. Like this. Next, we want a 0 here. Right, to get a 0 here, we're going to use the operation and say, okay, because of space, I'm just going to write it here. So you can say row 2 minus 4 row 1. We say row 2 minus 4 row 1 because we're trying to get a 0 here. Okay, what is the aim of this matrix? Is to get the numerical values of A, B, C, and D. That's all. Alternatively, as your school says, then we can be able to say that you can look for vectors that are multiples of each other here and pay them up. Okay, which is much easier. So, okay, the first row, it's easy. Then this one, minus 4 plus 4, 2, 12. Then you have 0, 2, 1, 0. Then you have 0, 0, 0, 1. Right, this is fine. Now, let us get this next one. So at this point, you can be in a position to do whatever you can. Okay, I want to find the numerical values. Do whatever you can. Let us just say we're going to take this one. 1 minus 1, 0 minus 3. 1 minus 1, 0 minus 3. 0, 4, 2, 12. 0, 4, 2, 12. 0, 2, 1, 0. 0, 2, 1, 0. 3 zeros and a 1. Like this. Okay. Okay, the aim is to see if these things is to reduce this into reduced row echelon form. In principle. So there's already a 1 here. We need a what here? We need a 1 here. So okay, yeah, some books use an error. So you put 1/4 of row 2, meaning you have this one here. Okay, 1/4 would be that. 3 0, 2, 1, 0, 0, 0, 0, 1. Okay. Now this one is going to be row 1 plus row 2. Need to get a 0 here. Okay, add these two. It's 0 here, 1/2, 0. 0, 1, 1/2, 3. Row 3 minus 2, row 2. 0, 0, 0. Yeah. Yeah. Minus 6. And this one is 0, 0, 0, 1. Okay. Proceed here. We want to see pivots here. I want to determine the pivots and see the pivot columns in this matrix tell us that we get a basis if we take. Okay, yeah, the pivots will tell us which vectors to take from here. Okay, so now we can see that obviously we need this one here. So we can then say row 4 plus row 3. 0, 0, 0, 0. Minus 1/6, row 3. 0, 0, 0, 1. Okay, so you have pivot 0 up. Okay, I need to put a 1 here. Right, so we're taking this, we're writing this second row, which is 1 here, 1/2, 3, and this one is 1, 0, 1/2, 0. Anything we can do now? Let us check. Anything you can do right now here to row reduce? Right, is any row reduction possible? Yes. Okay, but we're able to see the pivots anyway. But now we can be able to get a 0 like here. Okay, it's not very necessary because you're under exam conditions here. So like you can say row 3, row 2 minus 3, row 3. So 1, 0, 1/2, 0, 0, 1, 1/2. Okay, yeah, 0, 0, 0, 0, 1, 0, 0, 0, 0. All right, now this is what we have. Okay, what is the answer? Okay, now this is already in reduced row echelon form. Right, so it is in reduced row echelon form. It is in reduced row echelon form. And then with the reduced row echelon form, what then do we do?
We solve.
What do we do? We solve. Okay, okay. Now we are able to make the following because we're able to get the numerical values. Right. So in principle, we need to get it, but now I'm just going to use exactly the method that your lecturers are using here to use the pivots. But now, once again, you would say this is A, B, C, D. In principle, you would actually make the observation Okay, yeah, this is very interesting that I found myself doing this. I found myself doing this. I found myself doing this, but I must indicate that in principle, the last column of zeros can as well be included, but yeah, it's left out in your course. Your lecturers leave out the last column of the zeros. Okay, so because of this, because in principle, then when you want to solve this, we have taken these things here, then we must have the zero column here on the end, because the 0, 0, 0, they must be there. But yeah, I can see that there's a tendency to leave them out, and that is how my lecturer was doing it as well when I was still learning this course. So in this point, what then you are doing is you can write these as the equations you're getting. You can write these as A plus 1/2 C is 0. B plus 1/2 C is 0. D is 0. Okay, can write like this. And then now at this point, this is immediate that these vectors are linearly dependent. Okay, because we want all these things to be 0. We want A to be 0, B to be 0, C to be 0, D to be 0. But they're not. Okay, this is what we're getting. So the pivot columns in this matrix, so we're able to get, this is right here. Right, so we're able to get like this one, which is 1, 0, 1/2, 0. 1, 0, 1/2, 0. Okay, 0, 1/2, 0. 0, 1/2, 0. And then we have 3 zeros and a 1. 3 zeros and a 1. And then 4 zeros. 4 zeros. Okay. So now what do we do with these things? Okay, what we do with these things now is to find a basis for the span of this. Right, we're then saying the pivot columns in this matrix tell us that we get a basis if we take, so let's write that one down, the pivot. Right, what you call the pivot columns in this matrix. Right, so the pivot columns in this matrix tell us that we get a basis for the span of S if we take, right, if we take the, all right, so now let us look at the pivot columns. Okay, this one contains a pivot, so it's a pivot column. Right, so if we take the first, right, and also the second contains a pivot. So take the second, right, first, second. And then what else right now? And the last one, well done, the fourth one. Thank you so much. First, second, and fourth. Right, and fourth. Right, just write a bit clearly here. All right, and fourth. First, second, and fourth. And fourth, polynomials. Right, polynomials in S. That is to say, B, the basis we want. That is to say, B, the basis we want, would contain the first, which is exactly 4x cubed plus x squared. Then we take also the second one, which is exactly minus x squared plus double x. And then we take the fourth one, minus 3x squared plus 1, like this. So that is, this one is a basis. It's a basis for the span. The span of what? It's a basis for the span of S. Like that. Okay, let us look at the next question. Right, because we're to find a basis B for the span of S, and we can see that therefore this one is the basis for the span of S. And then now let us see what else we have here. What else we have here? Next question. Right, we solve. Now we want to find the next question. I want to solve the next question. We've already got that. Right, we're moving to the next question. No chance. Okay, what is the dimension for the span? What is the dimension for the span? Right, we recall that the basis, or a basis, right, so a basis for the span of S is given by B, which we said the first, the second, and the last. So, all right, the dimension obviously depends on the basis. Right, so we have 4x cubed together with x squared, and then we have minus x squared together with 2x, and then we have minus 3x squared, the last one. Okay, what is the dimension? Okay, the basis is that, so that the dimension of the span of S is exactly 3. Well done. Dimension for the span of S is exactly 3 because we count the basis vectors. And there are 1, 2, 3 basis vectors there. Right, okay, let's look at the next question. Let's look at the next question. We're moving to the C part. Okay, here's C. Here's C. Right, answer the following questions, giving reasons for answer. Right, so is this one a member of the span? Justify your answer. Is this one a member of the span? Well, if it is a member of the span of S, right, we need to, it means therefore that this one, okay, so you take the 1, 2, 3, 4, A, B, C, D. So you take these ones to be real numbers, so that now this can be written as A times 4x cubed together with x squared, B, which is minus x squared together with 2x, C is 2x cubed together with x, D is minus 3. Okay, so you try to write the vectors in a combination of the vectors in S, and the last one is minus 3x squared plus 1. Okay, because is this a member of the span? We write it as a combination of the vectors in S, and then we analyze what that means. Okay, so what does this mean? It means that you have x cubed together with x squared, which means you have 4a plus 2c. We're looking at the cubes. There are 1, 2 cubes. And then we have x cubed. How many quadratics? Right, there's a here for the quadratic, minus b for the quadratic, and then minus 3d for the quadratic, and we have x squared. And then what is the linear things? The linear things is 2b, c, and then you have x. What is the last thing? You have D. Well done. Right, and this means that we can equate the things. 4a plus 2c is equal to the coefficient of the cubic term. And then this one, the quadratic, is a minus b minus 3d is equal to the quadratic one. And then the last one, you have twice b plus c, it's zero because there's no linear. And then d equals 0 because there's no constant. Right, so with that mentioned, we're able to have the associated matrix, which is exactly, okay, yeah, we have A, B, C, D, and then we shall put a line. Okay, now we put this augmented matrix because we have non-zero numbers here. Right, so for the A, it's 4, B is not there, C, it's 2, 0. This one is 1 for the A, the B is -1, 0, -3. The 0B for this one, the C is 1, 0. Okay, yeah, the right-hand side is 1, 1, 0, and then 0, 0, 0, 1, 0. Okay. And what is the conclusion about this? Okay, we want to find the values of A, B, C, and this is the case. If the values of A, B, and C exist, it means that this vector is an element of the span, but this one has no solution. Why? Okay, has no solution. Why? Because the last equation is telling
It's
us,
false.
yes, it's the first equation. So has no solution because we can see
It's not
right here, which has no solution since the last equation. Right, so the last equation, or the last, you can say the last row. The last row implies that 1 equals 0, which is false. Which is false. Which is false. Because of that, we're able to then say hence the x cubed together with this one. The x cubed together with the x squared themselves, this one is not in the span because it's problematic. It's not in the span of S because if it were in the span of S, it would produce solutions that exist. But at this point, we have a false row. This bottom row has a false implication that 1 equals 0, and 1 is not equal to 0 in mathematics. And therefore, we conclude that the x cubed with the x squared is not in the span. Let's look at the next question. Let's look at the next question. Right. Now, is there a polynomial in P3, polynomial P of X in P3, such that if you take the basis B with the union of that polynomial, it's the basis for P3? Okay, that's a very interesting question. Right, that's a very interesting question. Right, okay, let us recall that the basis B we got, what was the basis B we got? We said we take the first, the second, and the last. The first, the second, and the last. Okay, what is the, okay, if this is the basis, what is the dimension of this? What is the dimension of this? Right, so it will be 3. It will be 3 because there are 3 vectors here. There are 3 vectors here. And what is the dimension of P3?
It's 4.
Of P3 is 4, which is 3 plus 1. All right. So, well, because of this, then in mathematics, there's a theorem that says every basis whose dimension is less than the actual space can be extended by basis extension. Yes. So is there? The answer would be yes. Right. Yes. We can. But by basis extension, the basis can be extended because you see we have fewer elements than P3, so we can extend it to be equal to P3. So yes, we can, for instance, take P of X. P of X to be X cubed together with X squared. Like this. Okay. For instance, take P of X to be X cubed together with X squared. Okay, this can be anything, but we can take that which is allowed, which is possible by the basis extension theorem. Basis extension theorem. Okay, this is possible by the basis extension theorem. So the basis that has few elements than the actual vector space, then you can extend it to a basis with the same number of vectors as a basis for P3. All right. All right. So I'm looking at our time, and our time is like 21:41. We started at
Are we
about.
done with this question?
Yeah, we're done with this question because the next question.
Okay.
The next question is something else. It is on. Yeah. The next question is 6, and question 6 is on ranks and things. Okay, so and obviously we're done with that question 5, but also yeah, so I'm just looking very carefully, so yeah, we could continue, but we can just take a break. We are not we still have time. So we studied about 1920 odd.
20.
Yeah, around 1920. So we're good. I mean, we estimate the time to like 2 hours on average. So we actually are fine. So, right. So we must thank you for joining us. It was really, really awesome having this discussion today. Right. Obviously, we are going to be stepping up our discussions, making sure that we get more problems to practice. And once again, we shall be taking our problems from existing material, past assessments and exams, but also we'll be taking this from like the study guide. I have a study guide you sent to me, and yeah, because yeah, and then anything else that we're going to include would have to be very similar to that, so that we don't waste time looking at things that do not matter. You know, we are trying to practice with like things that are relevant, the kinds of things, because any examiner would often use the kinds of things that are there either in the past exams or in the study guide, but can hardly bring something from nowhere. I mean, you would not expect that. There has to be, these things must bear some resemblance, some similarity with what exists. Right. We thank you for joining us. Okay, we record these discussions once again. I'm planning to have these videos sent to you. If all things go well, I think that I'm gonna send a video tonight. Okay, yeah, right. So, but if I say
because
yes.
You didn't send the last one, so please send that one as well.
Yes, I'm gonna send the previous one as well. Okay, good. I will.
Thank you so much.
Because that's fine. Thank you so much. Thanks so much for joining us. Right.
Thank you.
Let us meet tomorrow. You advise us on the time. It can be like 6, 7.
6, 7. Yeah.
Okay, it's up to you.
6, 7 is fine.
Oh, all right. Yeah, you'll just confirm which one is okay with you. Then we can take that. We'll take that one. Either 6 or 7 is okay with us. So yeah, you let us know what time suits you best. Right. Otherwise, yeah, from us, thanks a lot then. Until tomorrow, have yourself a good evening. We shall send the recording. Goodbye.
Okay. Thank you. Bye.
Thanks. Goodbye. Right.